generated moment. This applied moment is m and induced moment is m by 2. So this moment is half of this m. So this 1 by 2 is nothing but our carryover factor. So again, if I explain you, then at this end, this is the applied moment m, and here the moment gets generated. Little bit this moment is m dash. So, but we know that the value of m dash is m by 2. So this 1 by 2 is nothing but your carryover factor. This 1 by 2 is nothing but carryover factor. Now, if you want to define the carryover factor is nothing but, now see here, I will write now. Carryover factor is, it is the ratio. Basically, carryover factor is the ratio. The ratio of which quantity to which quantity? The ratio of generated or induced moment. Okay, the ratio of induced moment. Where it is induced? At fixed end. Okay, at fixed end. Divided by applied moment. Divided by applied moment. So we can write here carryover factor. Carryover factor is, here in this case our induced moment is nothing but it is m dash divided by applied moment is m. So m dash is nothing but again it is m by 2, m upon 2. So m will get cancelled. What do we get? 1 by 2. So this 1 by 2 is nothing but carryover. Now we will write down the definition of this. So the definition of this is, it is the ratio. As we are seeing here, it is shown to you that carryover factor is the ratio. So it is the ratio. It is the ratio of the moment produced or generated. Okay, one and the same thing. produced at the point or we can say at the joint. Here instead of saying it is produced at point B, we will say that it is produced at joint B. Okay, joint to the moment, it is nothing but your carryover factor. Then after the carryover factor, the important thing is the stiffness. After carryover factor, the important thing is stiffness factor. Okay, or simply it is called as, many of times it is only called as a stiffness. So stiffness we can define it as, it is the moment required. It is the moment required. It is the moment required at simply at one of the end of the beam to produce unit rotation at the end. To produce unit rotation at that end. So the basic for stiffness is, we know that P is equal to K into delta. Okay, so therefore delta is equal to what? So therefore instead of delta I will take K. K is nothing but stiffness. Force is equal to stiffness into deflection. So stiffness is equal to what? P by delta. Similarly, instead of force, if the moment is there, then M is equal to K into theta. For force, deflection is there. For moment, theta is there. Okay, so K is equal to nothing but M by theta. Okay, so here if theta is equal to 1, then whatever may be the moment produced there, it is equal to the stiffness. Okay, so it is defined from this formula. This definition is connected to this formula. This definition is connected to this term formula. Here you can put theta is equal to 1. So this definition says that it is the moment required at one of the end of the beam. Okay, so this is our required moment required M to produce unit rotation if theta is 1. So M by 1 is equal to K, so K is equal to M. So in this way, the stiffness factor is defined. Okay, so the stiffness factor depends upon the far end of the beam. Okay, far end of the beam. Now, if I tell you here fore end or far end. Okay, this is the fore end or far end condition, and here I will write stiffness, the value of stiffness. For first thing, number 1, if your fore end condition or far end is simple support, oblique, hinge, or roller support, or roller, your stiffness is 3 EI by L. Stiffness is 3 EI by L. Second thing, if fore end or far end is fixed support or intermediate support, then the stiffness is 4 EI by L. Then the stiffness is 4 EI by L. And there is one more condition is there. If your fore end or far end is free. Okay, in case of cantilever, the far end is free. So if it is far end is free. If it is free end, then the stiffness at that end is 0. Okay. If it is free end, then the stiffness at that end is 0. So this is the important thing related to stiffness. This 3I by L and 4EI by L, how does it come? This I will tell you in the next lecture, that is in lecture number 2 of the moment distribution method. For time being, you remember this. These are the fore end conditions. So fore end conditions means what? Now if I draw over here diagram for support number 1. Okay. Now suppose this is the beam. This type of beam is there. Okay. And here the moment is applied. Here the moment M is applied. Due to this moment, the deflection of the beam is like this. This is the deflection of the beam. Now this is called as fore end or far end. This end B, it is called as fore end or far end. Now this fore end or far end is what? It is now here simple support. So in case of simple support, if the fore end is simple support, then the stiffness is 3 EI by. So I can write over here M is equal to what? M is equal to here. It is 3 EI by. Okay. The value of M and K is same. As I told you over here. The value of K and M is same because we put theta is equal to 1. What is the whatever may be the value of M, same is the value of K. Okay, so M is nothing but K. So I can write over here K is equal to what? It is 3 EI by L. If the fore end is simply supported. Now this is simply supported. Similarly, if we take another case, here simple support is there and here fixed end is there. Now moment is applied over here M. The deflection of the beam is this. Okay, so again this point B is the fore end. Now your fore end or farther end, this is fixed. fixed support is there. Then the value of M here you can write fixed support or intermediate support. Stiffness is 4 EI by L. So this is 4 EI by L. So I can write here K is equal to, what is the value? 4 EI by L, as M is equal to K. And P and you can say that if a cantilever beam is there, suppose this type of beam is there, cantilever beam. Third case, cantilever beam. This end is free, end B is free. Here it is end A. So in this case, the deflection of the beam will be in this way. This is the deflection of the. So here your stiffness, value of stiffness is 0. Here your value of stiffness is 0 at free end. I am telling you, not at fixed end. Remember this. Free end it is 0. Okay. So after this, now the next part is distribution factor. So the next part is distribution factor. Next one is distribution factor, DF. Okay. So distribution factor for a member at a joint is the ratio of the stiffness factor stiffness factor of a member divided by total stiffness of all the members meeting at a joint. So first we will write the definition, then I will tell you what that definition says. So the definition for this is a distribution factor for a member at a joint is the ratio of, see here, the ratio of stiffness, the ratio of stiffness factor for that member to the total stiffness of all members meeting at a joint. So now this is the definition. Now let us see what does it says. A distribution factor for a member at a joint is. Now from here the real definition starts. It is the ratio of stiffness factor for the member to the total stiffness of all members meeting at a joint. Now suppose I will take here one point. This is point B. Two members are meeting at this point. Okay. So here, suppose this is point A, this is point C. So member AB and member BC is meeting at point B. Okay. So the stiffness, like the stiffness of member AB is KAB and the stiffness of member BC is KBC. Okay. Now what is the total stiffness at joint? Now total stiffness at joint B. What is the total stiffness? It is KAB plus KBC. This is the total stiffness. If I add these two stiffnesses, then I will get the total stiffness at joint. Okay. Now we know the individual stiffnesses. For member AB, its individual stiffness is KAB. For member BC, its individual stiffness is KBC. And we know the total stiffness. Total stiffness is the addition of these two stiffnesses. Now if I want distribution factor. Okay. So distribution factor of AB. Okay. So distribution factor of AB is I want that. Then Here I will write D. So now DFAB is the distribution factor of AB. Similarly, I will write here DFBC. DFBC is the distribution factor of BC. Now if I want to calculate the distribution factor of AB, what does its definition says? If you want to calculate the distribution factor of a member, it is the ratio of stiffness factor for that member. So now if I am calculating distribution factor of AB, then I should take the stiffness factor of that member. Stiffness factor of that member means stiffness factor of AB, whatever may be the stiffness factor, that I should take into the account. Ratio means we should divide the quantity by the total stiffness of all the members meeting at a joint. So what is the total stiffness of this joint? We have already calculated the total stiffness is, it is KAB plus KBC. This is the total stiffness. Okay, similarly, if I want to calculate now the distribution factor of BC, then distribution factor of BC is nothing but stiffness of BC. Okay, as per the definition, ratio of stiffness factor of that member. So stiffness of BC divided by total stiffness of all the members meeting at a joint. So all members here, two members are meeting, AB and BC. So take their stiffness as total stiffness, KAB plus KBC. So in this way, the distribution factor is calculated. If instead of two, if three members are there, we will take that third stiffness into our total stiffness. Okay, so in this way we have to calculate the distribution factor. Let me tell you for three members. Now suppose this is again the same joint is B. Now here is the member BC, here is the member BA. Suppose one more member is there, BD. So let us say that the stiffness for member AB is KAB, the stiffness for member is KBC, the stiffness for member BD is KBD. Now if I calculate the distribution factor of AB, so distribution factor of AB, now if I calculate D of AB, so the distribution factor of AB will be stiffness of that member. As per the definition here, it is given that stiffness factor of that member. First we have to take that. So the stiffness factor of AB is KAB divided by total stiffness of the members meeting at that joint. So for at joint B, 1, 2, 3, three members are there. To take the stiffness of all these three members, so it will be KAB plus KBC plus KBD. Similarly, distribution factor of BC, if I want to calculate, then it is KBC divided by KAB plus KBC plus KBD. So in this way, we work out for the distribution factor. Then some standard formulas are there for the fixed end moments of the beam. That also I will tell you in the next lecture of this moment distribution method. So the summary of this lecture, if you remember this one, the most important thing, what we have learned in this lecture. So we came to know that moment distribution method is basically used to calculate for fixed end moments. Correct? It is the indirect method. Indirectly, this method applies slope deflection equation. So it is the method which is used to calculate the fixed end moment. Second, what we study what is carryover moment. Okay, we study here the terminology is carryover moment. Then we study in this lecture what is carryover factor. Then we gone through the stiffness factor. We know that if the farther end or fore end is fixed, then stiffness factor is 4EI/L, and if it is hinged or simply supported, then it is 3EI/L. You know this, 4EI/L and 3EI/L. When the fore end is fixed and here fixed or intermediate also. Remember this, intermediate support, we treat those support as a fixed support, intermediate, and all remaining supports here, simply support, hinge, ruler for 3 by. Okay, after that will be distribution factor. Okay, distribution factor. What is distribution factor? Its definition, then how to calculate the distribution factor. Okay, so distribution factor in short, if I want to write, then I will write here stiffness of member divided by total stiffness of joint. So this is the formula for distribution factor. So these things we are knowing now. In the next lecture, I will tell you that in this example of carryover moment, I have explained you that m is equal to m by 2. That if you applied m moment at any end, then the generated moment at the other end is m by 2. How does it come? That I will derive in the next lecture, that we will see in the upcoming lecture. Then also I will give you the formulas of standard cases for the fixed end moments, and we will solve the numericals based on it. Okay, so hope you enjoy this introduction first lecture. Thank you.